I'll give you the microphone. You're doing the introduction. I will take that mic. Yes, you take it.
Mobile.
You have a phone? Can everybody hear me in the Zoom? Just a text message would be good.
Yes, we can hear.
Okay, thank you. Thank you. I didn't see actually who was. Maybe Professor Acharya. It was Professor Acharya probably. Right. Okay. I'll just wait for 2 minutes. I'll just wait. Yeah, I'll just wait. Yes. The mail reached the students, right? Today? Yeah.
I also don't. I'm a backbencher.
Yeah, of course. I'll just request the Zoom audience and the YouTube audience to wait for 2 to 3 minutes. We are just going to start. That's schedule.
Oh, he's a member?
Yeah, he's a new guy.
It's the same fellow. Okay. Yeah. Shevin.
So this is
He's from where?
Kerala, Abhimanyu.
No, but which institute or?
He's actually working for industry in
okay.
machine learning. He's getting quite a bit of salary and he wants to do PhD.
Very interesting.
So, obviously,
where is he working? Which city or something?
I think it's in Bangalore. I have to check. But he's working from home. That's what something I have to check.
Of course, nowadays everybody is working.
Yeah. Need to check with him whether he's good. Okay, I'm going to actually start by welcoming all of you to this edition of the NSF Wednesday Colloquium. So I would like to mention to those who are joining for the first time, the NSF Wednesday Colloquium is actually as old as TIFR itself in terms of discussing science and within the institute. This idea germinated from our founding director, Professor Homi Bhabha, who ensured that all the natural sciences faculty actually met together once a week on a Wednesday and listened to an eminent scholar who was visiting TIFR that day and have discussions after the talk. So this particular colloquium series has been beneficial to all of us historically, and it's really a pleasure and honor to host this. So today we have Professor Bhal Joshi from NCRA, which is part of TIFR, giving us his first colloquium at TIFR. Professor Joshi is, of course, well known to many of us in TIFR, except me. I got introduced today, and I'm lucky. But I'm sure there are people who connect with him through via being students or colleagues, and I am lucky to also have my colleague from the Department of Astrophysics and Astronomy, Gopakumar. Yeah, Professor Gopakumar, to introduce Professor Joshi. So, Gopu.
Thanks a lot, JD. So it's actually a great honor and pleasure for me to introduce Bhal Chandra to you. I'm sure that many of you already know him, but I'm going to add to those who are new. Bhal Chandra is Supremo of Indian Pulsar Timing Array. So he's numero uno Pulsar astronomer of India. So he is currently the IP International Pulsar Timing Array Steering Committee's chairperson, And we are actually going through difficult times. You will see the reason in the coming months. And he is instrumental in creating this collaboration Indian Pulsar Timing Array, and that actually uses unique capabilities of Gmrt to inaugurate and establish firmly something called nano-Hertz gravitational astronomy in the coming years. Bhal Chandra is a graduate of IIT Roorkee, and actually we had a meeting there, and he was very happy to be back in Roorkee. Thereafter, he actually went to industry with Tata's, having a very good salary, decided to bunk that and join NCRA to pursue, his interest in astronomy back in '93. And he did his PhD with Vivek and then went on to do postdoc in Manchester, and then came back. And so he has been, his expertise are on pulsars and various aspects of pulsars. I mean, from the emission properties, binary pulsar. He was actually one of the discoverer of double pulsar, which actually provides one of the best test of general relativity up to date. And he is also very much onto science education. He ran successfully radio astronomy program, winter school in radio astronomy for a decade in NCRA, which we followed up with Pulsar Observatory for students in Uti. And that's essentially where we kind of try to, talk about an Indian Pulsar Timing Array consortium. So additionally, Indian Pulsar Timing Array is an integral part of something called International Pulsar Timing Array. And these days we are actually, combining our resources and efforts with European Pulsar Timing Array to see in the near future discovery of nano-Hertz gravitational waves. And, in the coming months and all that, you will hear more about it. And this is a collaboration of 40 plus and so many institutes. And Bhal Chandra is the person who actually visualized, implemented, draw all of us crazy. As you can imagine, some of the younger people here will justify to that. So without much further ado, I will hand over the stage to Bhal Chandra.
Okay. Hello. Can everyone hear me?
Yes.
Yeah. Okay. It's a pleasure to be here once again, and good evening to everyone present here, as well as those of you who are online. And many thanks to Gopu, who has been a dear colleague, for his very, very kind words. Sometimes words which are not true. I am not neuro, but fine. Okay, so he's been very kind. And the efforts which I'm going to talk about today are a culmination of a decade-old collaboration between both of us. And many thanks for that, Gopu. And essentially, what I'm going to talk about today, and great thanks to Jyotishman and to TFR for inviting me here to share these few words about this very exciting field in which Gopu, myself, and our colleagues have been working for last 7 to 8 years, using the niche capability of the Giant Meter Wave Radio Telescope, as Gopu mentioned, in a collaboration of about 40 plus members, to open up a new window to the universe. And this has only been possible, which I'm sort of at the beginning acknowledging, because of the hard work of these 40 plus collaborators which we have, as well as, most importantly, the staff and the members of UT Radio Telescope and the Giant Meter Wave Radio Telescope, whose exceptional professional work has made our quest possible. So I want to acknowledge them right at the beginning of the talk. Okay, so I'm going to introduce you today in my presentation to this new messenger to the universe called gravitational wave. And the ultra low frequency spectrum of this messenger is spanned by the pulsar timing array experiments, where these gravitational waves have yet not been detected. So gravitational waves have been detected, but not at this particular frequency band. So after explaining these PTA experiments very briefly, I will sort of introduce you to the efforts of the Indian Pulsar Timing Array experiment and our recent results. And I'll put our recent results in the context of the state of art in the gravitational wave astronomy as of today. And I'll conclude by discussing the prospects of a discovery in the near future, as well as potential for future post-discovery science. So a brief history of gravitational waves is in order here. So Newton in 1685 sort of for the first time defined in his laws the gravitational force. But it was not until the formulation of electromagnetic theory in 1865 by James Clerk Maxwell, where Maxwell for the first time speculated on the gravitational fields as well as the existence of the gravitational waves, that the topic of gravitational waves actually sort of took birth. While Einstein was, and of course, this topic was further taken up by a brilliant electrical engineer, Heaviside, who actually proposed the first theory of gravitational wave radiation. While Einstein was formulating his special theory of relativity in 1905, Henry Poincare showed that masses, orbiting masses, can produce retarded potentials due to the quadrupole moment of these particular masses. Later, Abraham actually worked out in detail the theory of gravitational wave radiation, which he got some elements wrong. He sort of came up with quadrupolar gravitational wave radiation, which was waves which were longitudinal in nature. Of course, in the meantime, Albert Einstein worked out the details of his general theory of relativity in 1916. But at that time, Einstein didn't believe in the gravitational waves. It took him another 2 years to do the calculation to sort of show that gravitational waves are a natural consequence of general theory of relativity in 1918. Only to later repudiate it again in 1936 with Rosen because of, partly because of a mistake in the coordinate system, which both of them sort of ended up doing. And it took another 20 years for Pirani and others to rectify these things and finally established the theoretical framework or the theoretical existence of these gravitational waves. But from the first conjecture to the actual indirect detection of the gravitational waves, it took another 60 years. So it's a very, very long story. And as you will see, long is something which is the theme of all of our experiments. So this indirect detection was in the discovery of the first double neutron star system by Hulse and Taylor in 1975, where Hulse and Taylor showed that the loss of orbital energy from this double neutron star system exactly matched with the expected loss due to gravitational wave radiation. And this is illustrated in a later paper by Weisberg et al., where you see a 40-year record of the agreement of the prediction of the general theory of relativity and the points which are the measurements of that. And since then, this effect has been verified in more than 15 double neutron star systems. But this was an indirect detection. The direct detection, you must have seen, many of you must have seen this plot again and again. It's a 7-year-old plot of in the previous one. Previous one, this is the shift of a periastron. So your orbit is shrinking because of the gravitational wave radiation. And from the general theory of relativity, you can predict how much amount the periastron would shift. And you can actually do the measurements using pulsar timing, which I will talk about later on, to actually figure this out. Okay. So this plot, all of you have seen many, many times. So this was the discovery of the first direct detection of the gravitational waves by the advanced LIGO in a binary black hole coalescence. And this actually heralded the era of the gravitational wave astronomy. Finally, firmly established the gravitational wave as I said, almost 60 years since the first conjecture of that. So that's the brief history of gravitational waves. Now, analogous to electromagnetic spectrum, this slide shows the spectrum of the gravitational waves. The waves which were discovered by LIGO are on the higher frequency band here, which are sensitive to the terrestrial detectors like advanced LIGO and so on. The pulsar timing array, on the other hand, which I'm going to talk about, are sensitive to this ultra low frequency spectral regime, which is from few nano-Hertz to few microhertz and so on. And in that sense, one can see that the pulsar timing array astrophysics is complementary to the high frequency astrophysics by a terrestrial detector like LIGO, or a space-based detector which sits in between, which is called as ELISA. Much in a similar way, radio astronomy is complementary to, say, optical astronomy, and both these astronomies provide complementary pictures, very different pictures of the universe. So opening this new window, so gravitational waves have only been detected here. Opening this new window is important to sort of extend the gravitational wave spectrum to get an alternative picture of the universe.
Can I ask a quick question? So
yes.
here, Jyotishman. So this entire spectrum will be, for the gravitational waves, will be broad enough that you will see in those frequencies also in 10 to the power minus.
Yes, so it all depends on the sources which you are talking about. So the gravitational waves are produced by orbiting masses.
Okay.
So it depends on the orbital periods. So the frequency is the periods.
Okay.
When we are talking of high frequency systems, we are talking of stellar mass black holes, or we are talking of neutron stars, which have orbital periods much shorter. And we are actually talking of transient sources there. We are not talking of continuous wave sources, and I'll explain that later on.
Okay.
Here we are talking of supermassive black hole binary systems, which reside in the centers of the galaxy, which have a period of the order of years and so on. So, and of course, if you go further down, you are talking of things like cosmology, inflation, and so on, where the periods are even more longer. So this entire thing starts from about 100 attohertz and goes up to kilohertz. That's the frequency range.
Okay, thank you.
So, pulsar timing array is actually not a terrestrial detector, it's a celestial detector, which uses an ensemble of pulsars distributed uniformly across the sky, more or less isotropically, to detect these gravitational waves in the vicinity of the Earth, and that I will qualify at a later point of time. And again, the frequencies are nano-Hertz to microhertz, because we are talking of periods of the sources which are producing of the order of few months to few tens of years, which corresponds to a frequency of nanohertz. And in terms of wavelength, it's of the order of a few parsecs, 10 to the power 17 meters, and so on and so forth. So these are the numbers which are relevant as far as the PTAs are concerned. Okay. Now, since the sources involve periods of the orders of a year and decades, the sources would be supermassive black hole binary systems. But more importantly, by design, these experiments will have to be decade long. So you can't expect to detect this in a year or even in a month and so on. You need to do a continuous sustained effort. And this is very demanding as far as the patience is concerned, both of the people involved as observers in this experiment, as well as, since we are going to make observations using radio telescope, as well as the patience of the telescope time allocation committees, and we continuously keep on having all kind of run-ins with this kind of thing. So it's difficult to carry out these experiments. The sources, supermassive black hole binary system, the typical prototype of that is a very large galaxy. And this is one particular source which all of you here must be familiar, because Gopu must have talked about them several times. So OJ287 is a blazar at a redshift of about 0.3 and so on, which was believed to be formed by a merger of two galaxies, with the supermassive black holes at the centers of these galaxies capturing each other, making a binary system with a period of the order of 12 years or so, which is exactly in the frequency range where we are sort of talking about that. And this model is more or less firmly established by work done by over last 120 years actually, but most of the work coming in the last 30 years by Mauri, Gopakumar, his students and colleagues, Lankeshwar and others. And I am sure you guys must have heard this, at least the astronomy, astrophysics members would have heard about this many sort of times. And essentially the way it has been established is by using electromagnetic messenger, where the flashes, periodic flashes of light from this particular source has been sort of attributed to the orbital variation of this entire thing. So this is a typical prototype source. And okay, so that's just an animation by Gopu's student Abhimanyu, who has actually made a fantastic animation to show the flashes which are periodic, and they are double flashes. Okay, so they have put in a lot of theory to actually try this, and I think more or less one can believe that these are because of the periodic thing. So this is the best possible candidate for a PTA. So while OJ is a very nice candidate as a source for the PTA, it's an individual source, individual continuous wave source, and it's a very weak gravitational wave source. So you can't actually detect them. Okay. It's going to be very hard to detect them in gravitational waves. But what you can do is you can detect a signal from an ensemble of these sources. And the hierarchical structure formation models which have been worked out, they suggest that the galaxies merge. And whenever galaxies merge, the black holes harbored in these galaxies will become gravitationally bound and form binaries. And over the history of the universe, you will have a large number of these binary systems, each of them emitting gravitational wave at their orbital frequency. And they will be distributed in a cosmological scenario all over the universe. So they will be more or less isotropically distributed. So if you do a random superposition of an ensemble of gravitational waves from all of these black hole sources, you will form a background. And this background is called as stochastic gravitational wave background. So as far as PTAs are concerned, the most promising candidate for gravitational wave detection is a stochastic gravitational wave background. And this background will have a typical spectrum, which was worked out early in this century, around 2000 or so, which depends on a range of parameters. What are the orbital periods of the black holes going into forming this background? What is the number density and the function, the number density as a function of redshift, which is going into this? What's the history of the merger of galaxy evolution and so on? Eccentricity of this system, are they circular or eccentric and so on? And how much is the proportion of eccentric system compared to circular system in that? And most importantly, the dynamics of the orbital period evolution itself. So as the black holes move towards merger, there will be all kind of frictional forces, dynamical frictional forces in the galaxies because of stars and dust and so on. So that whole history has to be encoded in trying to determine this particular spectrum. And the spectrum looks something like this. And qualitatively, basically the later part of the binary evolution is faster. When the orbital periods are larger, the binary evolution is slower. So you have more power at lower frequencies because you have more binaries sitting in the lower frequency bin as compared to the higher frequency bin. So that's the typical 2/3 spectrum with Jaffe and Becker worked out in almost 20 years back and so on. And that is what is sort of what PTAs are trying to detect. A word of caution here that this kind of background can be found by other means also, and I'll just briefly list those means at a later point of time. The difference between a galaxy merger scenario background versus other backgrounds is the slope of the spectrum, which is given by the index alpha, and different alphas could correspond to different backgrounds. So this is not the only spectrum which is possible, but this is the most favored sort of a picture which we are talking about.
Can you go back to that data, please? Yeah, how do we understand this? So you have these lines that you have the red curve has and the blue curve. There are two data sets that I see.
Okay. Yeah.
And then there are some fits. I guess the green is the fit, or the red and the opposite. Is it opposite?
So these are for various kind of dynamical evolution. Okay. So as you see, the color is viscous disk. So if you assume that your binary system is moving through a disk galaxy which has a viscosity,
Okay.
that viscosity is going to change the time scale over which the evolution is going to take place.
Okay.
Similarly, you can have stars scattering in the center of the galaxy, and depending on the scattering cross sections, again the time scale of the evolution of the binary can change. And again, eccentricity. So as I said, some of these could be eccentric. So for all of these cases, you will have the corresponding spectra. So the spectra need not be the same.
Okay.
And the reason, so this line is the 2/3, which is a simple-minded galaxy evolution scenario, prevalent way back before the SDSS and other surveys in 2000. So based on that, you get a 2/3 power law spectrum.
Okay.
But as you can see that these points are the limits, upper limits put by the PTA experiments already. Okay, in terms of the number there denotes the number of years over which the limit has been derived. So it's coming very close to this, and we have not detected gravitational waves. Okay, so obviously there must be something wrong in the theoretical picture. So these different models invoke different dynamics to try and bring this spectrum down. Okay, so that you explain the non-detection of the gravitational waves. So that's what are the details of that picture, which I skipped over because I thought, but since you asked,
I was wondering what that noise pattern is on the blue trace, the blue and the red. So that's data that you get
that is informed by galaxy surveys.
Okay.
So when you say that I have a certain amount of viscosity, that would depend on some electromagnetic observations, and there will be error bars on that.
Okay.
So the model itself will have an error bar.
Right.
So that band which you see there
Right.
is the sort of 2 sigma, 3 sigma error bar on the overall spectrum.
Okay.
Okay. That is important because if I push these points further down at some point of time and I still don't detect gravitational waves, how do I explain it? Okay. So this is all what has been happening in the last 4 to 5 years, and this is actually a good case how PTAs are already, without discovering gravitational waves, are already constraining the structure formation models to a large extent and the dynamics of the galaxy evolution.
And if you were to see the gravitational wave, what will it do to the spectrum? How would you?
Yeah. So you see these turnovers, okay?
Right.
So again, this can be the x-axis can also be interpreted as the time of the experiment, because the longer you observe the pulsars, the lower is the frequency which you are going. So we are somewhere here, okay, 17 or 18 years.
Okay.
If we continue to extend this to 2030 and beyond, we will be start probing this part of the spectrum.
Okay.
That's where a lot of interesting physics occurs. As you can see, there are curvatures there and so on and so forth. So if we detect gravitational waves, one of the post-discovery signs would be to continue observing and improving your spectrum so that you can start constraining other parts of that. Okay. So there will be further milestones in trying to constrain the galaxy evolution models in the future to come. So discovery of the gravitational waves by PTA is not the end. Of course, we all want it immediately, but once that has happened, there's a lot of post-discovery science which can come, and all that is encoded in this spectrum.
Okay, thank you.
So as I said, that spectrum can be, so this is only from galaxy evolution. Okay, but the same gravitational wave background can come from other sources, and I have listed 2 of them. All of these different type of sources, so there is completely different physics as far as those sources are concerned of the gravitational wave background. They will give a different alpha, okay, flatter or some other kind of alpha. So the spectrum can actually even probe and constrain some of these. So this is background. Individual sources, as I said, are not very strong. They are fairly weak. But it is always possible that you may find a source which may outshine the background. So first thing which you have to do is you have to find a source which is much stronger than the background, and at different frequencies the background is also different. So your source strength, which depends on chirp mass and so on of the other parameters of the source, will be different, but you can find that, and that will be a continuous wave detection. And even interesting detection, and especially from younger PTA experiments like in PTA, is a transient source. And that transient source would be a coalescence of one of the binaries. In coalescence, these are supermassive binary systems. There will be a very powerful burst. And that powerful burst will actually distort the space-time permanently. And that is what is called as gravitational burst with memory, and that would be very interesting to detect. Even a 1-year experiment can do this, but of course the probability of this kind of an event is extremely rare. So you have to be very lucky to sort of detect this. So these are some other different types of sources. Okay. Now the pulsar timing array uses pulsars. So an introduction to pulsars, brief introduction is of order here. Radio pulsars are highly magnetized rotating neutron stars, and they are very good clocks, basically because of their immense rotational kinetic energy reservoir, which can be depleted very, very slowly. So their timing does not change very much. And PTAs time these clocks to by using a technique called pulsar timing, where you compare the prediction of the pulse time of arrival when the pulse has arrived from a rotational model of the star by keeping track of the number of rotations of the star. So you predict the TOA and then you compare with an observed TOA. The difference between the two is called as residual, and this residual you can minimize in either Bayesian or a least square sense to refine the parameters of the model which you started with in the first place. And that model may have rotational, positional, or binary parameters all involved. In fact, there are something like 30, 40 parameters which can go into this. But it also has properties of the interstellar medium. So the pulse gets dispersed by the electrons, free electrons in the interstellar medium, and it also gets scattered by inhomogeneities of this electron distribution. So those will also sort of will also give you the properties of the interstellar medium. And finally, this noise-like white noise-like thing, which is sort of left out after removing all these things, that is where the gravitational wave sits. So essentially, the amplitude of the gravitational wave is comparable to your instrument noise. So the noise which you are getting from the telescope. So that's another reason why this is a very challenging experiment. Okay. And you have to have a fantastic instrument to do that. You need to tune the instrument to do this kind of a thing. So this is the basic idea behind pulsar timing array, but let me go a little bit more in detail. These are the 4 gentlemen who actually developed the concept of pulsar timing array right from early 70s and so on. It was Sazin in 1978 who first realized that apparent frequency of a pulsar clock varies due to perturbation in the space-time metric by a passing gravitational wave. So he was the first person to propose that pulsars can actually be used for this. And Duttweiler soon later sort of developed this to measure the closure density of the universe using some 3 or 4 pulsars. Okay, so they were the initial pioneers. But it was actually Becker, the gentleman here, who did a lot of work, and along with Hellings and Downs for the first time said that the best way to detect the background would be to use an ensemble of radio pulsars. And he was the person who coined the term pulsar timing array. He worked very doggedly for almost 2 decades before his death in 2006 to detect these gravitational waves. And similar work for last 2 decades has been done by Professor Dick Manchester in Australia, who founded another experiment for doing that. So those were the 2 pioneering efforts. And what they sort of proposed in very short terms is as follows, that the gravitational wave signature in the is basically seen in timing because the gravitational wave distorts the metric around the Earth, and it distorts it in such a way that the pulse time is either retarded or advanced by a very small amount of by a very small quantity. And this retardation and advancement essentially manifests itself in terms of a fractional change of frequency, which is given by the expression here. And in this expression, so that is the geometry in which the gravitational wave is passing, and you have a pulsar which is in this direction for a given polarization. You can sort of show that this is what the fractional change in the frequency will be there. The term H here is the characteristic strain, and you can have that near the Earth, which is sort of denoted in blue, which is called as the reception or Earth term, or you could have it somewhere near the pulsar, which is denoted in red, which is called as the emission term. So these are the 2 important terms here. So what Becker, Hellings and Downs showed is that the the emission term is uncorrelated across the ensemble of pulsars, whereas the Earth term is correlated. So why this is important? This is important because, as I said, they wanted to use radio pulsars because they are fantastic clocks. Their clock stability is very high. But when I say they are fantastic clock, does not mean that the clocks are really fantastically stable. Pulsars do show a slow wander of their spin frequency over several years, which is known as timing noise or red noise. And the time scale is comparable to the variation because of the gravitational waves. So if you use only one pulsar, you are never sure whether it is the timing noise of the pulsar or it is the gravitational waves. On the other hand, if you use an ensemble of pulsars, as Don Becker proposed in 1980s, the red noise of individual pulsars in the pulsar term will be uncorrelated over the entire ensemble. So you can sort of eliminate that. Whereas the perturbation which is caused by the gravitational wave near the Earth will be correlated across this entire sample. So you can actually look for this correlation. And if you find a correlation, you are reasonably sure it is nothing to do with pulsar. It is something to do with the metric near the, in the vicinity of the Earth. So this correlation, Helings and Down worked out in terms of this correlation. Yeah, sure.
You are saying that the gravitational wave essentially distort the space
Yes.
around the Earth. So it will also, like the motion of these photons, lights, that it will also influence all those kind of signals that we are getting.
Right. So that is what happens. The pulse is a photon. It's an electromagnetic messenger.
Yeah.
So a small perturbation in the metric is going to actually change the speed of the, or change the apparent arrival time of this photon. Okay.
I see.
So the pulse, which is a collection of photons from the pulsars, will either come earlier or it come later, and that delay in time will be proportional to whatever is your perturbation. It's very tiny, but there will be a signature there.
And you think it's a perturbation of the space to the
Yes,
space?
yes,
Oh,
yes.
Okay, I see.
So one is assuming that this delay is happening because of perturbation of space. That delay can happen because of many other things.
Absolutely.
Yes. So those are the noise sources, and I'll come to one of those noise sources, which is very important, and it is where the Gmrt's contribution is all about.
Yeah, I was thinking the source is different. Not really thought about the space gets distorted and that gives you.
Actually, this is much more tiny than many other sources. Okay, so you have to account for all of those before you say, okay, this is gravitational wave. So it's not a it's a difficult and challenging task.
But I mean, do you think that just curious? So if you are distorting the space, you mean that still the light moves in the straight line, or
No.
I mean,
No. It's not. It's not. It's something like Shapiro delay. So if you have a massive body, the space-time is curved around the massive body. So if your photon is passing without that mass, it will come faster. Whereas the photon is coming because from the space-time near the mass, then it will come slower. So that delay is what Shapiro. This is an effect which Einstein never proposed. Okay, Einstein never worked out Shapiro delay. It was Shapiro who, in 1960s, actually worked that out. So it's a delay exactly like that. But it's very tiny, and you are right that there are many other sources which can do the same kind of things. They are covariant. So you need to separate out each one of them, and that's one of the challenges in this experiment.
So if I understand the description right, these perturbations, it's a constant ongoing phenomenon, right? It's not a very occasional thing.
Depends on whether
you have a background, right? So,
yeah, for background, it's a constant, it's a wave. So your space-time is actually fluctuating with the wave frequency.
Like it's, what I'm saying is,
but it is constant for a background. For a transient source like burst with memory, it is not.
Right. But did I understand you right that the burst frequencies will also be in the same range, right? 10 to the power minus 7 to 10 to the power minus 9.
Yes.
So is it still possible to separate the burst from the constant background?
Well, so the first thing is burst is coming from coalescence. Those events are very, very rare, so unlikely to be seen. That's one issue. The other issue is that they are going to be much more powerful. So they will, I think they will sit in different parameter spaces. So if and when we are able to do that, we might be able to do that.
No, I understand. Thank you.
But as of now, most of us are focusing on the background.
So the way it happens is that the pulsar has a specific frequency. That frequency starts now slowly increasing in a very constant manner. And
Or
that's-
increasing.
Yes,
Yes.
and that's because of the memory. Because the memory can be shown to be kind of linearly increasing with channel. It's a constant thing and you integrate that. So it's slowly and that, and you will see it on many pulsars. That's very important.
Correlated again. The signature is very well predictable, and I think that's what Subhajit and Gopu are trying to work on. Because for us, it's very important. For MPTA experiment, if this happens, say, next year or something, we will probably detect gravitational waves before other PTS detect. Okay, but unlikely.
Is part of this correlated.
Correlated. So, okay. So I need to go a little bit more in the details of the timing. So this delta nu, this fractional change, this is an expression for one pulsar because your tracking signal is coming only from one pulsar. Okay. But the pulsar timing array is an ensemble of pulsars. So you will do a delta nu by nu measurement for each of the pulsars. So when we are talking of correlation, we are talking about correlation between the fractional change in the spin frequency averaged over the entire ensemble of the pulsar. So that is what the correlation is. In actual practice, it's not done in frequency domain. It is done in the time residuals. So that is a matter of detail.
I mean, it doesn't involve interaction among
Pulsars. Yes, yes.
So it involves.
No, it does not.
It
It does not.
Okay.
So that is why the pulsar term is ignored.
Okay.
Because you assume that they are uncorrelated. And the interaction between these two photons is only happening because of the gravitational wave. That is where the correlation is.
So these perturbation, does it depend on the gravitational frequencies
Yes, of course.
and how it depends?
How?
How it depends on the gravitational frequency? Perturbation.
No. So basically, if you recollect this, so this is the overall spectrum of the background. So it's not one monochromatic gravitational wave which we are talking about, okay? Because the background which we are looking at is an average over several black holes. So they will give you a spectrum like that, okay? So there will be frequency bins of each of these. And corresponding, so you could sort of think of the spectrum as a collection of several monochromatic waves. Each will sort of perturb it there, and the superposition of that is this spectrum overall.
Yeah, thank you.
Can I ask a question, basically?
Yes, Alok. Yeah.
Yes, Alak, good to see you or hear you.
Good to hear you. You mentioned that the transient sources are going to be very difficult to detect because they are very infrequent. Now, this is actually a statement which sort of should be sensitive to what is the sensitivity level that you can your timing array is still sensitive to transient events, meaning how far away can the transient events be and still you will still be able to detect it. Because if you can go very, very far away, then the frequency of these events will also start increasing. So what is realistically where do these events have to be detectable by?
You are very right, and I think this is some work to be done. And since you have asked this very nice question, I would encourage Gopu to sort of work out on some of these details. So you are right. The probability of a detection depends on the distance, and that distance depends on the luminosity of the event. So you need to actually go back to the drawing board and figure out how many such black holes exist. What is their Z redshift distribution, and what is the likelihood for each of that? And then short answer to your question is I don't know. Okay. I don't know exactly what it is, and it is dependent on the sensitivity of the PTA. So if you have a more sensitive PTA, say 1 nanosecond PTA, you can look much farther and you will be able to detect more of these events. For the current sensitivity, the probability is very unlikely, but this is again a hand-waving answer. I think this needs to be calculated properly.
May I pitch in? Alok?
Yeah, sure.
So Nanograv has done actually this. Shami and others were involved. So this is a bus with nonlinear memory from the black hole mergers. Unfortunately, the distance reach of that is around a gigaparsec. And we know that there are not many supermassive binary black hole merger out that distance.
Yeah, gigaparsec. That's very, very nearby.
Yes. So this is, but in the case of SK era, which is essentially end of this decade, that can become several gigaparsec, then things get more interesting. And for example, FAST with this, very precise timing and very recent data set, KJ thinks that they can go further by a factor of 2 or something like that. So,
yeah. So essentially, we are at 100 nanosecond precision, Alak, right now. So the sensitivity which is afforded by that 100 nanosecond, this is very, very unlikely that we will detect anything like that. But all the PTAs are trying to move towards 10 nanosecond timing, and some of them, Nanograv and others, are sort of reaching those kind of levels, where I think somebody has to do a calculation. So I don't think the final word on this has been written. So
What's the limitation of,
yeah.
What's the limitation of Indian PTA to go towards that higher sensitivity?
100 nanosecond. We are in the same regime as Nanograv.
Yeah, but I mean, you're saying that you can improve. I mean, other people are trying to improve.
We can improve. So we are also trying to improve.
So what is basically the most critical limitation?
The limit is well, there are several limits. Some of them are instrumental, some of them are astrophysical. So the instrumental limits are the timekeeping. So in Gmrt, we still have a maser clock. We have a maser, but we don't have a clock derived from maser. I'm hoping that in next 4 months, 5 months, we will be on maser completely. So that is instrumental. There are also astrophysical things. So the sensitivity depends also on the level with which you can remove the RSM noise, the level with which you can characterize the red noise, and so on. Now, those are the factors which every PTA will suffer from, not just in PTA. So the improvement which, say, Nanograv or EPTA makes also applies directly to us in that sense. Okay. So the astrophysical constraints, I think all the PTAs are moving together in improving the precision. Instrumental, of course, in PTA will have to work on their own instrument, which is Gmrt, and which people are. So Gmrt, I think the time and frequency group is working on this problem, this thing. So yes, I think 10 nanosecond will be achievable, certainly by all the instruments. But 1 nanosecond, where this becomes a much interesting possibility, is not possible before SK. So we have to wait till 2028, 2029 for square kilometer array to be able to reach that kind of precision.
Okay, thank you.
Okay, so yeah, so the difference. So coming back to this, so we use pulsar timing to get the difference which fits these models. And amongst the factors which you need to account for is the dispersion delay in the interstellar medium, solar wind and solar system dynamics. These are the astrophysical noise sources, like what Alak was asking. So this is one of the important astrophysical noise sources. And I put it in red because this is very relevant for Indian pulsar timing array experiment. This is our bread and butter to sort of model this. Okay. I have already moved ahead. Yeah, sorry. Correlation. So this is the form of the correlation, and this is known as Helling and Down overlap function. So essentially now I have explained that there are 2 requirements to claim that I have detected gravitational wave in the PTA spectral range. One is what I showed earlier, which is the spectrum. So you should get the spectrum because that is what characterizes the stochastic gravitational wave background. And the second is this overlap function. And this overlap function, one can think in terms of like an antenna pattern. So you have an isotropic source, which is the stochastic gravitational wave background, which excites this pattern, and that is the pattern which the PTA sort of measures. So that's another instrumentalist way of thinking about how the pulsar timing array operates. Now, this checklist, so this is all very easy said than actually done, because the precision required is 1 part in 15 in timing measurements. So since our PTA is typically having an arm length, which is from Earth to a pulsar, which is of the order of a parsec or so, that means that you need to have some kind of a precision, timing precision of 10 nanosecond in, if you sort of interpret this arm length or 1 part in 15 of this arm length in terms of light travel time. So that's the kind of precision which we require. As I just now told Alak, we are somewhere between 10 to 100 nanosecond. We are still not at 10 nanosecond. And if you want to do even weaker sources, we have to go to 1 nanosecond kind of precision. The other problem is that the ultra low frequency nature, the nano-Hertz nature of the gravitational wave, means that you have to observe these forces over decades. So some experiments are going on for 27 years now. And you have to do that because you want to populate each bin of the spectrum, right from the low frequency to high frequency. The high frequency bins get populated very fast, 1 year, 2 years. We also have that spectrum, but the low frequency ones, you have to go for a long period of time. And this requires painstakingly tuning your radio telescope as well as your probes, which are the pulsar sample, to a very high degree of precision. And that means that you have to design a very good PTA. For that, you need some instrumental requirements like a very sensitive radio telescope and a time and frequency standard, which is precision at the radio observatory, which is again what I was telling Alak, that we are trying to improve that. At the same time, you need astrophysical sources which are good clocks. So you first of all need pulsars which are distributed all over the sky so that you can get that correlation function. And you need pulsars with very stable light curves and pulsars with highly rotational stability. And this is a very big ask from the astrophysical thing. So to form a good PTA still is a challenge. And you need pulsars on lines of sight where you don't have a complicated interstellar medium to produce a noise source there. So these are the basic requirements. And they are easily said than done, because out of about 430 millisecond pulsars known out of a sample of 3,300 pulsars discovered as of today, only 75 fit the bill. Okay. So we have a very tiny fraction of pulsars which fit this bill. And even these 75, they suffer from random wander of their spin rotation frequency, which is called as timing noise or red noise. And in addition, you have these other noise sources, the instrumental noise, the timing noise, solar system. Our solar wind itself produces an effect which is much larger in the delay. So as you were saying, there are other sources, and these are all noise sources for us. So we need to be able to, and they all vary over years. So these noise sources are covariant with the gravitational wave signal. So we need to have very good models of this if we want to extract the gravitational wave out. Despite all these challenges, 4 major PTA experiments are operating in the world. The Parkes Pulsar Timing Array in Australia, which uses the Parkes telescope, the North American nano-Hertz Gravitational Wave Observatory NanoGrav in North America, and the European Pulsar Timing Array, which operates using European telescopes in Europe, and our own experiment, Indian Pulsar Timing Array, which uses the Gmrt in India. The number of MSPs, the salient features, and the time span of each of these PTA experiment is listed there, as well as their geographical distribution on this particular map. All these PTAs, they pool their data together, and they pool their data together in what is known as International Pulsar Timing Array Consortium. And that data is supposed to be the most sensitive PTA data, and InPTA also does that. As Gopu mentioned, InPTA is the chair of the IPTA this year. So that brings me to our own experiment, and the rest of the talk, mostly I will discuss what we have got from our experiment. This Indian PTA idea was conceived in a discussion when Dick Manchester visited Bengaluru in 2012, and we started a feasibility experiment in 2012 and 2013 to check whether we can get the kind of precision which are required. So we are much younger compared to the other PTA experiments. And then we started a pilot experiment with the legacy Gmrt, the older Gmrt. So I, along with Gopu and Manjari Bakchi from IMSC, the three of us, we started this initiative in 2015. And in the meantime, the Gmrt upgrade was going on. So when the upgraded Gmrt new capabilities became available, Yashwant and myself, we started another experiment to check the feasibility of timing with the upgraded Gmrt. So with all these, this initial period, 2013 to 18, was sort of testing grounds. Okay, we were not really sure whether we can do something fantastic there. But since 2018, the INPTA is operational using the upgraded Gmrt. And all the observations and analysis is conducted by an Indo-Japanese collaboration, which has about 40 scientists, including about 10 PhD students as part of that. And we, as part of the experiment, we regularly monitor 15 pulsars every 2 weeks. And our main goal is to characterize and distinguish the slowly varying interstellar medium induced noise. So we are focusing on a very specific noise source for gravitational wave, which also happens to be a very, very important noise source.
So can I ask a quick question? Just an administrative question. How does that differ from the other pulsar timing arrays spread around the world? So your particular focus is specific set of pulsars, or is it
no,
or you are also overlapping with?
It's an overlap with the other PTAs, and for the reasons which I will describe a little bit later. So there's a specific reason for the overlap. In fact, all PTAs have overlaps.
Okay.
So about 25 to 30 pulsars are common in all 4 PTA experiments.
Okay.
Nanograph has a much larger number of millisecond pulsars. They go up to 70, 75 pulsars.
Right.
PPTA works over 25 pulsars, and EPTA works about 40, 50 pulsars and so on. Okay. So it's all a function of telescope time. So in GMRT, we have only a specific amount of time. We would also like to go right up to 40, 50. But what we have done is we have chosen the best sample, which will sort of keep us well in the game, and still we can contribute significantly to the LPT.
Thank you.
And there's a lot of work which our collaboration members who can testify. Yes? Yes, Alak.
Yeah. So suppose there is limitation of telescope time on GMRT, but if you were to go primarily on, let's say, ORT, would that situation improve?
No, so ORT has a problem that ORT is a very small bandwidth telescope. So see, why we have shifted to GMRT is because we have 200 megahertz, and I'll explain why in a little while. So ORT's capabilities are good for high cadence, but they are not good for sensitivity.
Okay.
So we do use ORT. So even now, some pulsars are being observed, but it's only for cadence purposes, not for sensitivity. Okay, so the goals which I said, they gel very well with the unique and niche capability of the upgraded GMRT, in the sense that UGMRT is a low frequency radio telescope. Now, why they match so well with the capability? Because pulsars are steep spectrum sources. They are bright at lower frequencies. So you can get more signal to noise ratio at low frequencies. But even more important thing is that if you want to characterize the interstellar medium, these are propagation effects which are very strong functions of frequency. So they are very dominant at low frequencies, nu to the power -3, nu to the power -4, and so on. And as an illustration, I've just shown 2 plots. So this is, if you have a very tiny 1 part in 3 error in estimating the dispersion, you can see as a function of frequency, which is plotted on the y-axis here, the arrival time of the pulsar, or the delay of the pulse arrival, can be very significant, and that is what is shown here. This is phase in x-axis and y-axis is just the frequency. So as a function of frequency, a very tiny error can be manifested very easily. So this is because of dispersion in the by the free electrons between you and the pulsar. But the electrons are also not homogeneously distributed. They are inhomogeneities, and that produces scattering of the electromagnetic signal, which broadens the signal. And that broadening is also a function of frequency. Again, the y-axis is frequency and the x-axis is phase. So you can see the pulse width varies. And both these things are not constant as a function of time. Both these quantities, they vary slowly over year, 2 year, 3 year time scale. So variation of dispersion and scattering over several years is covariant with the gravitational wave. The effect on the pulse arrival time is orders of magnitude larger than the gravitational wave. So unless you take this into account, you can never claim that gravitational waves have been detected. You have to remove this somehow or other. So before GMRT came online, people were doing this with high frequency observations. They were observing at 1 gigahertz and above. The precision at high frequency is not as high as when you go down to 300 megahertz. When we have come, we have given, as I will show later on, unprecedented precision in measuring these effects. And I think that is our most unique contribution to the International Pulsar Timing Array and the gravitational wave detection whenever it happens. So the unique capabilities of the GMRT, I can just sort of say a few words. GMRT, first of all, covers a 300 to 800 megahertz range, which most of the PTAs don't cover. So we are complementing the data from the other side. More importantly, we can do very high sensitivity observations. Apart from the brightness of the pulsars, we use phased arrays with new wideband feeds between 300 to 1400 megahertz. And we do this by using the interferometry nature of the GMRT instrument. Since it's an interferometer, there are multiple elements. So we can divide the GMRT into two co-located 75-meter equivalent telescopes. So the same telescope can become two telescopes, one at 300 to 500 megahertz and the other one at 1260 to 1460 megahertz. And we do this by using the new upgraded capabilities of the multi-band, multi-subarray and multi-beam feature option of the UGMRT. So this is very unique to GMRT in the sense that no other telescope has this kind of a thing. So this allows us to do concurrent observations at two frequencies. No other PTA does concurrent observations at two widely separated frequencies. So again, this is a unique feature of in PTA. Now, these niche capabilities are very useful for precision DM measurements and characterizing the effects of interstellar medium for precision timing and complementing other PTAs. So we have been doing this for 8 years, but as I said, first 4 years went into tuning the things. But in the last 3 years, we have had, apart from the gravitational wave science, other interesting results. So I'll just briefly mention, we did the first ever detection by a PTA experiment of a coronal mass ejection from Sun in 2019, and that was published as a paper. So these are intermediate results which are interesting and exciting by themselves, which we sort of published. We also discovered for the first time a profile change in a millisecond pulsars, and again this has been published. And we applied wideband techniques for precision DM measurement for the first time at low frequency. So these are three very important and main results which are not directly related to gravitational waves, but which came as a spin-off of this project.
May I ask one?
Yeah.
How the UT telescope, is complementing this UGMRT? Because is it functional at present, or
I don't know how to respond to the second part of the question, which I will probably sort of not respond to. Okay. But the first part of the question, I can say that UT has the same frequency, 325 megahertz, which we are using with GMRT. So you may ask, then why do it with UT? You can do it with GMRT. Okay. GMRT, on the other hand, is a proposal-based international instrument. So you have to, people propose for time, and there is a time allocation committee, GMRT time allocation committee, which allocates time. So obviously it's a general purpose instrument. It does imaging, it does various other kind of science, and this is one of them. It gets a huge amount of time on GMRT, no doubt, but it can't get the full time. So you can't do a dedicated thing there. which means that we have to design our experiment cleverly. In the sense, we have to have a good sample of pulsars, a small sample of pulsars. We have to monitor them at some reasonable interval, but we can't monitor it faster than that. OT, on the other hand, is a TIFR instrument. Okay, nobody else uses it, only TIFR uses it. So you can in principle observe the same pulsar every day. So you can observe it more frequently. And there is a study which showed that if you have a higher cadence observation, the sensitivity of your PTA goes up. So OT's role is not very sensitive, is not very good for all the effects which I am talking about, but the cadence can make up for it. Now, if OT continues to operate, it can do this. I don't know what will happen in future, so I rather not comment on that. Yeah. So while these are exciting and interesting results, I think the main contribution of InPTA is the precision DM measurements, which is in the first public data release, which we just made some 10 or 15 days back. So this will be the main contribution. So just to sort of illustrate some of these results, so our nearest star sun has several energetic events, solar energetic events. And one of them is a blob of plasma confined by magnetic fields, which it ejects once in a while, sometimes towards the Earth also. And these are known as coronal mass ejections. Sometimes multiple coronal masses are ejected, they interact with each other. And more importantly, coronal mass ejections or CMEs can interact with the solar wind. So sun has a wind and it can interact. In all such interactions, one thing which happens is that there is temporarily in that line of sight, there is an over density of the electrons. So since we are anyway measuring dispersion to a very high precision, we can measure this over density to a very, very high precision. And that is what is shown in this plot here, where you see this outlier. This is actually not an outlier. This is because of a coronal mass ejection which happened. And this is the first time a PTA experiment has detected a coronal mass ejection. This is the geometry of the thing. So there was a Earth-directed CME which interacted with the solar wind to produce this over density, which is what we sort of detected here. So this was a very interesting result, which we sort of published it here. And even in the solar community, they were very sort of excited about possibilities of detecting this. So like in OT, if we can do every day this kind of a measurement, this we were lucky. Okay, so this is serendipity. But in OT, if you can do this every day, then you can actually catch many more of these events and you can contribute to space weather, which has nothing to do with gravitational wave. Okay. So we were just showing that there is a possibility there. We are not doing that cadence. So this was an interesting result. The other was that the pulsars usually, yeah.
So what is the time of the order of magnitude?
This one.
Yeah.
This is of the order of half a year or so. So this pulsar 2145 comes very close to the sun also. And in addition to this kind of an event, you can also monitor solar wind on this. So it is possible to even, in fact, there are studies by EPTA and LOFAR, where they have actually sort of shown solar wind signature on this as well as several other pulsars also. So you will see an yearly variation. If you take a spectrum of these, you will see a yearly peak, which is the solar wind. So there is a lot of things which you can do with the PTA experiment, which are not really related to gravitational wave. So millisecond pulsars, am I running out of time?
That's okay.
Yeah. So what's the time like? How much time I have?
So at least 5 minutes.
Oh my goodness. Okay. So then I must rush. I was simply rush. So anyway, there were interesting results. And this is our first public data release. This is the sample which we observed distributed across the sky. And we have two important data products. One is the dispersion measure and one is the time of arrivals. So just to sort of, I'll skip over this. So we use two different methods for measuring this dispersion measure. One is to divide the two bands, 300 to 500 and 1260 to 1460 into narrow subbands, measure the time of arrivals and fit the precision DMs to that. The other one is what we call as wideband techniques, in which we use a principal component analysis to reconstruct a template, correlate this template over the entire 2D data of the band and get ultra precise TOAs and DMs. So these are the two techniques which we use. And this is just to illustrate the precision which we are getting. So the blue circles are showing, these are in fact the best DM precision ever in any of the PTA experiments. So that is, I think, the unique feature of the InPTA experiment. The blue circles are showing that we are getting about 1 part in 4 or 1 part in 5 measurements of DM uncertainties routinely for most of the pulsars. The red circles are showing our best DM measurements, which go as good as 1 part in 6. The typical PTA precision is few parts in 4. So we are 2 orders of magnitude better than many of the PTA experiments. So this is the typical time series, which is a product of this. This is a sample data product. What I wanted you to focus here is this is only from a 300 to 500 megahertz timing of the pulsars, and we already reach about 100 nanosecond kind of precision here. Why this is useful is because usually the pulsar timing array experiments work at high frequencies. There is no low frequency PTA. This for the first time sort of indicates that one can even build a low frequency PTA, which will be very good because you can have many more millisecond pulsars. Millisecond pulsars are weaker, but they are brighter at low frequency. So you can't have them in high frequency, but you can have them in low frequency. So this is an important result there. These are the timing residuals and some DM interpretation, which I'll skip over. Okay. So in the last 4 or 5 minutes, I will sort of put our results in the context of the overall PTA science. Why is in PTA data important for PTAs? Primarily because of this frequency range. Because this is the frequency range which is not there in any other PTA. So we fill a critical gap in the data sets of all the other 3 experiments, nanograv, EPTA and PPTA. And this gap will remain till 2028, even with the new telescopes like Meerkat and FAST. FAST also does not have right now a low frequency observing program. 2028, because in 2028, the square kilometer array, the next big telescope, will come at these low frequency. After that, our advantage may sort of reduce or diminish. And we are the only experiment which can provide precision ISM measurements, and models of this variation of ISM as a function of time are very, very important or critical to improve the sensitivity of PTA experiments as well as for the future things. And just to sort of show how incorporating these models improves the sensitivity are these plots. These are plots of timing parameters of some of the pulsars. So this is right ascension declination, the spin period, the parallax, and more importantly, the amplitude of the gravitational wave and the index, the power law of the gravitational wave. The red curves are the curves without incorporating the interstellar medium noise models. The blue curves are the curves when you incorporate these models. So this is simulated data. This is not actual data. So if you have a simulated data with injected gravitational wave, you can recover the gravitational wave amplitude by at least 7 orders of magnitude better. So that sort of underscores the point which I am trying to make, that the models which NPTA will produce will significantly improve the sensitivity of the gravitational waves. Yeah.
Yeah, so this is assuming a particular power spectrum of the
Yes,
signal.
yes.
But in principle, you are going to have
It could be different. It could be different. So actually, there is some ongoing work within our own collaboration to this has not been done very much because most PTAs don't have the precision which we have. So we are redoing this work.
I see.
And in that, some of these things would be very useful to sort of explore. Okay, so what is the current state of art? As I have already said that we can constrain models of galaxy mergers, but we can also do something about solar system. It so happens we don't know the orbit and masses of our own solar system bodies, and that leads to the solar system barycenter shifting by hundreds of meters. And you can even find unidentified massive objects. So this is what the PTAs have been doing. But the most exciting part, which has come in the last 2 years, is for the first time discovery of a common red noise process, which is like the spectrum which I talked about earlier by all the PTA experiments, including the IPTA combination of the data. And these plots just show the detection of the spectrum and the various type of different spectrum. These are the posteriors for that. What could not be detected in 2020 was the Helling and down correlation. So as I said, there are 2 things required for claiming the detection of gravitational wave. One is the spectrum and the other is the overlap function. The spectrum people have detected in 2020, but not the Helling and down correlation function. So in the last 1 year or so, which Gopu says we are having difficult time, we are actually advancing. So these data are all based up to 2015 and 16, not after that. So all PTA is now advancing the timelines so that the sensitivity can be improved. And this work is what is called as a 3P plus papers, which is likely to come out sometimes in March next year, which will have the latest full span timing data set. And unofficially, I can say that already we are seeing signature of the Hellingsson and Downs sort of a overlap function emerge out of that. So this is very different from LIGO, where there was a transient event and you saw a signal, chirp signal flush through. Here you have a continuous wave signal, which as the time span increases will slowly emerge out of the noise. And that is exactly what we are seeing. And our role in that is that we are combining our data with the European pulsar timing array, because they don't have the low frequency data. We don't have the time baseline. So it's a win-win situation for both the collaborations to combine the data together to form. Yeah.
How many pulses are common between INPTA and EPTA?
EPTA. So those are the 14 pulsars which I showed in the data
Okay,
release.
these are the common ones.
Yeah.
So
Well, except 2 of them, they don't use those 2 pulsars, but 12 pulsars are common.
So when you estimate the signal, correlated signal, because UGMRT is particularly good at low frequency,
Yes.
we use these tools to calibrate the red noise coming from ISM.
So the work which we are doing right now is to work out noise models, and this requires high performance computing, which we don't have in TFR now. So we are using a IIT Roorkee computer, Paramganga, which is a 1.7 petaflop thing. So you need to run Bayesian analysis to do all these things. So we are using our data to generate those noise models. These noise models will be fitted to the EPTA hopefully in the next 2 to 3 months. We still don't know. If they will be fitted there, we hope the sensitivity will improve. That's the game. Okay, so this is very current work. Okay, last I think next 3 months or so. So this is just to illustrate the data combination. All the high frequency purple points are the EPTA data. All the blue points are the INPTA data, and we can combine the data. This is frequency, this is the time. We can combine the data fairly well between the 2 PTAs. So this part has been accomplished. Now the next part is the noise modeling. So there are a lot of ongoing works, and future is very bright. I think I will end by saying future is very bright, and I'll leave you with the summary.
Thank you very much. Yes. Questions, and I'll just take student questions first. Daipan.
Right. So very basic question. So what are the factors that affect the correlation function? And if there are, say, new kind of interactions or new things, new gravitational wave sources, how can that be incorporated, to explain the correlation function?
So there are 2 things. That correlation function is essentially for an isotropic stochastic gravitational wave background. So anything which produces that background, okay. So in this case, the thing which we are focusing on is the hierarchical structure formation. So mergers of galaxies, that is what is producing the background. But it could be produced by other means, inflation, for example. Okay, so in cosmology, it can be produced. You can have cosmic strings, which are defects in the thing, and they will produce gravitational waves. The spectrum will be very different for that. And I didn't have time to go through those details here, but
Will affect the shape of the.
yeah, so the overall function will remain the same for them because it's the antenna pattern. Okay, so that's the first part that will affect the shape of the spectrum. Okay, now individual sources are different because individual sources are not isotropic, they are in one particular direction. So that will look like a bump in the spectrum, whatever is the continuous wave thing of that. And as Gopu explained earlier, for transient events like burst, it would be that you will have a correlated change in spin frequency of all of the pulsars. Okay, so there the correlation function would be similar to this kind of thing, because this is like an instrumental response of our array. So our instrument is all these pulsars together. Okay, so this is the response of that array. It has no physics significance. It's more instrumental in nature.
Was there a question there?
So this is regarding the perturbation in the vicinity of the Earth. What are the length scales of these perturbations?
So length scales will be of the order of the periods themselves. Okay, so we are talking of nano-Hertz. So So essentially the frequency and the periods are coming from the supermassive black hole binary orbital scales. It's the same kind of scales.
So what does it convert?
So that is where individual sources become very interesting. It's a different ballgame, which I didn't go into. There you can't ignore the pulsar term because the scale would be of the order of parsecs, which is your arm length. Okay. So you may be on the crest of the wave on one side and the other on the other side. Okay. But for the wave which we are talking of from the gravitational wave background, okay, you are only looking at the variation near the vicinity and you are ignoring all correlations on the pulsar term. Individual sources, you cannot ignore that. So that actually gives a good handle to find parameters of those supermassive black hole binary system. I didn't go into the individual sources because they are less likely, but Gopu can give a colloquium on that at some point of time.
So very nice talk, BCJ. That was great. So I have two questions. One is what sets the higher frequency limit on the on?
It's just the observation span.
No, that's the lowest.
So the cadence, 14 days cadence.
Okay, so if you get more details, you could push the.
Yeah, you can go into the Lisa band.
Okay. And the other question is, you mentioned that we can improve the solar system ephemerides and the masses and orbits and so on. So are there people searching for like Planet 9 lectures?
So there is a paper by Yanjun Guo et al. 2018, which sort of puts constraints on the so-called UMOs, unidentified massive objects in the solar system, which you can't see electromagnetically.
So eventually this will turn into, if you want to land on a planet, if you want to land on a planet, you need to know ephemeris very accurately. Right. So hundreds of meters, problem with barycenter as problem implication, if you try to go to Mars and eventually. So they're all going to bite back.
So we actually, after a lot of convincing and argument, we were able to convince JPL to produce new ephemeris. For years, JPL had not produced a new solar system ephemeris because they said, this is okay for us. Okay. But we had to argue exactly like what Gopu is saying. Ki tomorrow, suppose in Jupiter, you have to crash a probe to a meter precision. You cannot. And so the D430, which is the latest ephemeris which has come, D430 or 440, I think, 440. 440, the latest ephemeris which are, in fact, the 400 series has been very frequent. One after another it has come.
Okay. There is a question from Zoom, Professor Acharya. Could you unmute yourself?
Yeah. Yes. Joshi, thank you for the nice talk. I have a question about this. You said it is close to nano-Hertz gravitational wave discovery now. If after this nano-Hertz gravitational wave discovery, the field will move into you need a dedicated pulsar timing array, right? And what are is anybody thinking about that, or what are the plans for a dedicated pulsar timing array?
Yeah, that's a very good question. Actually, we wanted to have a dedicated instrument long back in 2016, and Professor Acharya, you will be aware that we have talked about that here also, called as Tata Pulsar Timing Array or TAPTA.
Yeah.
Unfortunately, that has not materialized for various reasons. One would like to build an instrument like that. That would be really great. But the trouble is that in another 7 or 8 years, the square kilometer array will come. So with square kilometer array, the sensitivity which you will get will be so enormous that building an instrument here may not be a very useful proposition.
Yeah, but SKA will not be available all the time, no, because so many other people would use for different purposes.
No, you are right. But SKA has this co-observing modes in which you can do all sky survey, you can do pulsar timing, you can do, say, a SETI survey, all of them together.
Okay.
So it will be possible to do that.
Yeah, all right. Thank you.
So for the kilohertz level thing like LIGOs, of course, if you have multiple gravitational wave detectors, you can locate things more accurately. in the case of pulsar timing arrays, is the work done by the measurements of two different PTAs? Does it give you any advantage in locating something in the sky, or?
Yeah, so you're right that as far as LIGO high frequency band is concerned, geographical distribution, having a LIGO India in India, for example, can give you a localization of the source to a large extent. In the case of pulsar timing array, I don't think that matters. The reason there was that the arm lengths for LIGO are very small, right? And Gopu can correct me. So the detector is very small. We already have a celestial scale detector. So moving on Earth from America to Europe to India does not actually change the situation very much. In case of LIGO, it does, because you have a 4 kilometer Hanford, you have a 4 kilometer the other detector, you have another 4 kilometers sitting in Indore, will give you an interferometry sort of calibration, which will localize much better.
That is terrestrial in some
This is terrestrial.
So this is terrestrial.
Yeah.
Last one.
Sorry, for the isolated events, most likely we'll have seen the binary electromagnetic window. So we already, and then the problem is the pulsar distance. There will be very important. Chandra is already on to doing VLBI for pulsars. That will come into play, but that's a different aspect.
So for multi-messenger, which I didn't have time to go through, which is the last slide here. So the era which we are moving is now multi-messenger astronomy. You had an electromagnetic messenger. You also had a particle messenger, which has not been exploited very well, but you primarily had an electromagnetic messenger. Now we have a gravitational wave messenger, and they are complementary. Just like wavelengths, these two give you totally different information. The gravitational wave messenger tells you about unseen masses, which you usually don't see. But it also, these unseen masses also produce electromagnetic radiation of all kinds, like OJ287, which produces those flash. So you don't see the black hole, but you see the flash. Okay. So when you observe the same source, like an individual source like this, both in electromagnetic as well as in the gravitational wave domain, the physics can be very rich, and that is exactly which this binary neutron star merger event of advanced LIGO did, because it explained so many things. These are all the 4 things which were possible because you had an electromagnetic observation of the same event as well as the gravitational wave event. So, and many more of these will happen in the LIGO era. Same thing can happen in the PTA era. So that is there. And as Gopu correctly pointed out, we can put the electromagnetic messenger to use to localize. And that will use the same principle as LIGO. You will have an interferometry over telescopes, which are, say, in India, China, Australia, and Europe. And happy to say that in last 1 year in Gmrt, we have actually demonstrated VLBI. So we have had fringes with Europeans, we have had fringes with Australians. In fact, day before yesterday, we had a VLBI experiment with FAST. So that would be the first Indo-Chinese VLBI experiment. So we are hoping that in a couple of years' time, VLBI with Gmrt will be possible, which is a completely new sort of thing. And Vishwesh Marpi from NCRA and Yashwant Preeti, we are all sort of involved in trying to bring this capability to Gmrt, and we can use that for individual sources.
Okay. So supermassive black hole binaries are most likely will be in AGNs. So electromagnetic, but AGNs are also copious sources of neutrinos. We are already have a hint of that. And Russian friends will tell you that they are planning to have papers with multiple epochs of neutrinos from such AGN. So this is going to get interesting down the line. So neutrinos, electromagnetic waves, gravitational waves, all from AGN.
One thing which I find very interesting in this whole science is that we go from solar system to cosmology on one hand, we go from electromagnetics to particles on whole. So in fact, what I would say, the opportunities are unlimited, whichever area you work in. Okay, you can contribute to gravitational wave science. So it's like that.
Thank you very much, Professor Joshi. This was a wonderful colloquium, and we all appreciate, based on this talk and the previous talk by Jairam, that the upgraded GMRT is doing so many wonderful things, quantifying hydrogen and telling us about evolution of galaxies, and then today about gravitational waves. So thank you very much. let us all walk together and have some snacks outside West Canteen. It's a good day, so we can have snacks outside. So thank you. Thank you, everyone, for joining in the Zoom. Thank you.